Okay, so I think the mistake I made, I'm making the conjecture here, is that when you change I remember that the only way I can think about is this, that my change of the limits from minus L/2 to plus L/2 messed up the formula. So let me try again using the other limits, okay? So let me try that. And hopefully this will work. Okay, so essentially then what I'm doing is I'm just saying that, this is I'm taking this as the period, right? Okay, so what we have is 1 over L, and my integral is from minus L/2 to 0. In that region, the integrand, this guy is plus 1. So I have e to the power minus 2 pi I and x over L d of x, and then minus, okay, keep that in bracket, minus 0 to L/2 e to the power minus 2 pi I and x over L, okay? Now, if I do this, then 1 over L, the first term is, and I'll be very careful so I won't jump steps, e to the power minus 2 pi I n of x over L, and this goes from minus L/2 to 0, and we divide this by minus 2 pi I n times L, 1 over minus 2 pi, and then we have minus e to the power minus 2 pi I n x over L divided by minus 2 pi I n times L, and here the limit is from 0 to L/2. Yeah, I think this is going to work. But so now we have minus I. Let's put that plus I, because let's take the I upstairs, divided by 2 pi n, and this L cancels out these L's. And then the first term we have e to the power, just one second. The first term we have e to the power 0 minus e to the power minus this minus and this minus will give me a plus sign, right? So we have, and this 2 and this 2 will cancel out. So we have e to the power I pi n. Okay? So this is my first term. And my second term is going to be, the first guy is e to the power, now this L and this L will cancel, this 2 will cancel this half. There is no minus sign, so this minus sign will stay there. So I get pi, I pi n. Okay, did I make any mistakes? I don't think so, okay. Well, if I do, please let me know. And then the second term is going to be e to the power 0, right? Okay. So what is e to the power 0? E to the power 0 is just 1, right? So I have I divided by 2 pi n, and this one will add up to give me 2 because there's a minus sign here. And then I get minus 2. There's a minus sign here and a minus sign here. 2e to the power I pi n, right? Because regardless of whether n is positive, is even or odd, e to the power plus I pi n, and e to the power minus pi n are the same number, right? Because if n is odd, then e to the plus pi n makes me come here. E to the power minus pi n, we just take different paths to the same point, which is minus 1. But if n is even, then we come back to the same point in this way or this way. Okay, so do you agree that these two numbers are the same, regardless of whether n is even or odd?
Yeah, makes sense.
Okay, so anyway, I mean, I can make mistakes, as you can see, but this is something I haven't done before, this particular limit, but let's just go on. So now we come to the moment of truth. Say n is a non-zero, even number. If n is a non-zero even number, then this thing is a positive, is plus 1, right? This factor. So then it's 0 if n is even. But if n is odd, then this factor is minus 1. And then this becomes, as Saif was saying, plus 4. So yes, our problem was the fact that I took a faulty. I did, without thinking, I changed the limits without changing the expression for the Fourier coefficient. Okay. So I'm running out of time, but I just want to can I take a few more minutes of your time, because I think I'm like very near the punchline. Is that all right?
It's okay by me.
All right. So essentially, what we have here is some, CNs, and the CN, I'm not gonna, this is going to be I 2I by pi n for n, odd, and it's 0 for n even. Now, what we can do is that, remember that the C's were the Fourier coefficients for the complex version of the Fourier series. And they were related to the real version by some relationships, like half of an, where n is a positive integer, bn for n greater than 0 and a positive integer. It was equal to, for n equals to 0, this was just a0. For n negative, this was equal to the complex conjugate of this with, the complex conjugate of this. Okay, now we can solve for this, and if you solve for this, then up to some numeric, I think, because I made a mistake, so there's a extra factor of 2 here. So we get the bn's are going to be, I think, 4 by pi n. Okay, whereas the an's are all 0. And this makes sense because if you go back and look at the expression for the Fourier series, I think the 0th one probably came with a half, the constant part, and then the cosine series, all the coefficients were n 2n pi x over L, and then the sine series were all bn sine of 2 pi n x over L. right? And we see that we are looking at a function which is an odd function. It's a piecewise it's a piecewise continuous function, but there are discontinuity at the junctures. Okay, so these are, but well, actually, it's a piecewise discontinuous function, right? Because there's a discontinuity here. So, but even then, it's an odd function, and therefore only the odd terms survive. Now we can plot these terms, and if you plot these terms, so these are the Fourier coefficients. So we are in the in the frequency space. So this is n, and this is, say, bn. Then we find that for b equals n equals to 1, we get some value. And for n equals to 2, we don't get anything. And then for n equals to, we find that for n equals to 3, we get 1/3 of this, right? So if so we get something like this. And then for n equals to 5, we get 1/5 of this, which is 1, 2, 3, 4, 5. So this is this. And then for n equals to 7, we get 1/7, blah, blah, and, stuff like that. So we can just, so this goes something like this, okay? So we can now write the Fourier series. And the Fourier series looks like phi of x is, I think it's probably 4 by pi or 2 by pi, I forget. Well, it's probably going to be 4 by pi. This is, this factor may be slightly different, but that doesn't matter. The leading term would be 2 pi x over L. And then the next term, the coefficient amplitude would be 1/3. And this will be times, so let's me not use x for times, but dot, sine of 3 times 2 pi x over L. And then the next term would be 1/5 times sine of 5 2 pi x over L. And this goes on forever. Okay, so this is the Fourier series. Now, if you were to now fire up your Mathematica and do this sum, you wouldn't be able to do the sum until infinity, right? Because Mathematica is a finite machine. You cannot do this sum infinitely, right? Is that correct? If you didn't know what the answer was, right? Suppose I just tell you this series. So you would have to do the sum up to some finite, So what you would have to do is you'd have to do a partial sum, the Sn. And it's only in the limit that, n goes to infinity, the partial sum goes to infinity, that this function would become your original function. But if you now plot the partial sum, what does it look like? And that's where a very interesting phenomena happens. And because it's a discontinuous function, what turns out is that at the discontinuity, you get an overshoot. So suppose that your original function was like this, but your partial sum, what it does is that it overshoots, and it does this at the discontinuity. Okay. So let me just try to do justice. So again, let me just try to, so the partial sum, instead of, say, going like this, and going like this, and going like this, what it does instead, it goes like this, and it overshoots, and then rapidly goes to 0, goes to the value that you're supposed to get. And then also there are phenomena like this. Okay. So this was first discovered by a British physicist, and unfortunately, history has hasn't really been kind to him. So I also forget his name, but it was rediscovered. This phenomena was rediscovered by the American physicist Gibbs. And this is known as the Gibbs phenomena. Okay, phenomenon. So what is Gibbs phenomenon? The Gibbs phenomenon is the overshooting of the partial sum when you try to use the Fourier series to model a piecewise discontinuous function. Okay, and this has a lot of applications, the Gibbs phenomena, and that's because if you're dealing with physical instruments and stuff like that, and suppose that for some reason up to some approximation your input is a discontinuous signal, right? Then because sorry, this is not a best. Yeah, this is not a best square wave. Let me draw a better square wave. And this also happens for sawtooth waves. Any waveform which has a discontinuity, a finite discontinuity. When you try to model it, at the discontinuity, you will find this ringing. I'm exaggerating it, but yeah, there'll be ringing. And that's because if you have some physical instrument, your physical instrument cannot be cannot be, say, sensitive of all the frequencies. So if there's a hard cutoff to your physical instrument, effectively, mathematically, what is happening is that you are cutting off this Fourier series. You're truncating it at some point, right? And therefore, what you're seeing in your instrument is not the input function, but some partial sum. And therefore, you will see this partial sum happen, okay? And, I have some Mathematica over here that I want to show, okay? So I'm just going to stop sharing on this device and start sharing on this other device, okay? Okay, can you see the Mathematica file? So what
Yes.
I'm doing here is I'm defining a function, f of x, and let's just change this to 4, yeah, 4 pi. And what I'm summing is I'm summing over 1 over 2p plus 1. So this is an odd number in the denominator. And within the sign, I have 2 pi x and then 2p plus 1. And I've chosen the period L to be 1. So there is no factor of L. And here I am choosing p to be all the integers from positive integers from 0 to n. And because what is inputting here is actually it's actually the odd integers. Odd. So now I'm using the manipulate function, and the amazing and a manipulate function is this fun function in Mathematica where you can see your plot change dynamically as you change n, one of the parameters. Here, what I'm plotting along x is x, along y is the function, and now it's showing you the function as a function of n, as a parameter n. N is 1. If n is 1, we see that it's a crude approximation to the square wave, okay? But if I change n, if I increase and see that it's trying to do, you see all the sign terms here, they're 0 at x equals to 0, right? So they have to work very hard to get to a finite value as close to 0 as possible. And that's how I think of it. You don't have to think of it like that. That's why they tend to overshoot. So as I'm changing n, as I'm increasing n, see that there is an overshoot, right? There's an overshoot, and then there's an overshoot and overshoot here. Okay, and as I'm changing, see there's like a Batman ears for the and this is essentially the Gibbs phenomena. Okay, and what is interesting is that this value, the overshoot, is a universal constant. Well, if universal, it's I think it's universal for all, all piecewise discontinuous functions, okay? Or I think it's a piecewise continuous because they're like, not discontinuous, piecewise continuous functions because within this region it's continuous, right? And that's the interesting thing is that this height, the limit to this height is actually it's a universal for all these kind of, sawtooth waves and stuff like that, okay? And of course it has, as we go higher and higher to n, see, it's not really going away. It's becoming thinner and thinner. It's becoming thinner and thinner. But see, there's tiny oscillations, right? So this is super interesting. Of course, I've just chosen n to x to go to 0 to 1. I could have chosen x to go from 0 to say 3, right? But if I go to 3, it'll be less visible. That's why I've chosen x to go from 0 to 1. I could have even chosen x to go to 0 to 0.5. Then that would even be better, I think. Let's see. Yeah. Maybe not. Maybe not. It's just too much. 1 is better. So yeah, so this is basically what I wanted to show is the Gibbs phenomena.